I would like to have my talk a little bit less formal, so instead of me talking for 25 minutes and then leave all the questions for last, so if anything I'm saying is unclear, just raise your hand and ask. If anything I said is wrong, then just raise your hand and correct me. Okay, so I will talk about basically these two experiments, trying to study the trajectories of photons. And I will start with kind of a general introduction to the topic and then go into the sort of details of the experiments. So let's start with a very simple scenario. I have some a source, like a single photon source, for example, and I'm sending a photon, and I receive it in some detector. So now what I really want to know is where have the photon, how the photon got from the source to the detector. Where did it went from? So of course, not all the photons that I send get to the detector, but the ones that does get to the detector, those I want to know how did they get there. So this is like the topic of my talk. What can I say about the way the photons got to the detector? So in general, like it could have gone anywhere, right? But now let's try to sort of restrict a little bit the scenario. So I'm putting a wall with one tiny hole, and now I'm sending a photon, and it hits the wall, so it doesn't reach the detector. I'm sending another one, and this one hit the detector. Okay, so now can we agree that the photon went through this hole? It's a question. Yes. So everybody agreed the photon went to this hole. And do you agree that this is a meaningful physical statement? Okay. So now, let's say I'm meeting a person. It's not a joke yet. I'm meeting a person, and this person says, no, you're not, the photon went to some wormhole and got to that detector without passing this hole. How can I show to that person that he's wrong? We are scientists, right? So I need to present some empirical data. So there's a suggestion? Block the hole, right? If I block the hole, I get no photons, then I know the photon went to the hole. Well, let's test if this is actually, we can apply this logic in other scenarios. So now I have two holes, okay? And you will know that I get these interference fringes. And what I do now, I'm moving my detector to be on a black spot. Okay, so now I'm sending a photon, nothing. Sending another photon, nothing. Let's try again, still nothing. 100% visibility, dark spot. No photon get to my detector. By the way, all the experimentalists, if you want to know how I got this visibility, you can talk to me on the break. Okay, so now I drill, just a minute, another hole. So now when I send a photon, I get the detector, right? So now, according to this suggestion, if I block this hole, I will not get any photons, right? So according to this logic, if I block this, the photon went to slit C, right? This is the kind of protocol that we all agreed upon a second ago.
That is wrong.
What is wrong?
The statement that the photon went to pole C.
Yeah, okay, this is, it's not a statement.
You said that I should raise my hand and say when it's wrong.
Yeah.
You said that.
Yeah. But if you look closely, this is not a statement, this is a question. Okay? My statement was that we all agreed that the protocol was if I block the hole and I get no photons, it meant the photons went from that hole. That was like kind of the consensus a minute ago. So I guess we need to something else to kind of to decide where did the particle went through. So now I'm basically consider this basic scenario. I have 3 holes, and now I will have 3 technical slides. What I want to do is to change the language from this like free space and holes to the language of beam splitters and mirrors. So basically, when I'm talking about these 3 holes, I'm just kind of preparing a superposition of 3 channels, right? So this thing is equivalent to this thing. And now, when I'm detecting here, basically, it's kind of a superposition of these 3 channels, but since I put it on the dark spot, I need to put opposite phase between A and B. So this thing is represented or is corresponding, equivalent to this system. So now I'm putting my 2 sort of mirrors, 2 sort of mirror beam splitter setup, and I get this kind of so-called nested interferometer setup. Okay? So now I'm coming back to the main point. I want to have some way to make physical sense of the question, where did the photon went through? So some other guy, which you might have heard of, Lev, had this idea. Let's send some sort of information from different points in the setup and see which types of information we get in the end. Right? So I'm encoding some information here, 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 and here. The way I encode the information, I put a mirror that is vibrating. It's shifting the photon left and right. And then by this split detector, I can see if I got this information. Okay, so the protocol is very simple. I'm sending information from 5 points, and I'm seeing which of the informations got to the end. So now when I'm sort of untuning the interferometer, I get all the information. Right? So I get, this is the frequency that this one is rotating, B, C, and so on. Now, what I do, or actually Ariel did, tune this interferometer to go down. So sort of putting this thing on the dark spot of the interferometer. And what happened? I get 3 peaks, but 2 are missing. I get the information from here, and from here, but I do not get any information from here and from here. Yes? So, if I understand, you're asking how these peaks correspond to this. So, as any physics, there are a lot of assumptions, but it's in principle, it's very simple. These mirrors just move the beam left and right, but it moves it very, very sort of slightly. Here, I'm just kind of measuring how many photons got a little bit to the right and how many photons got to the left. So let's say this is 1,000,000 and this is 1,000,001. I'm subtracting and getting 1. But then another time, instead of getting 1, it will be minus 1. So now I'm just looking at time, how this like 1 minus 1 sort of evolved. And I see the frequency at which I rotated this mirror.
Is the power spectrum
Is it okay? So I'm just getting this frequency by just Fourier transforming the readout from here. And what? Mine effect? Combine effect. Yeah, of course it's combined, but so I will get a very kind of noisy single, and I will just kind of Fourier analysis it, and I will get some very discrete frequency. So this is experimental data.
Is the power spectrum in arbitrary units, or does that mean something?
This is arbitrary units. So yeah, it depends.
Sorry. Are these 3 peaks obtained together with detection by the detector? So they are conditional on detecting the photon and you seeing in the detector the black thing.
So all the photons get here get detected by the spirit detector.
Right.
And then what I get is like yes, no, like left, right, over a long time.
But if the photons going from A and B left the system and cannot go to
this one, no,
so how the photons from A and B get to detector if they go out?
What do you mean? They get from here to here?
Yeah.
How?
Yes.
That's the question we're trying.
Okay.
Right? I don't know how photons kind of move. I cannot draw any trajectory coming from here to here.
I very much suspect that you won't see these 3 peaks together. But
no, this was not. This is one sort of data. The peaks were not sort of obtained separately. This comet might be correct for the next experiment. Okay, no, it's not you. Okay.
Excuse me. I know the answer. I discussed with Lev last time, but I don't talk about it.
What?
Yeah, I know the answer.
What's the answer?
Yeah, answer is very classical one.
The detector is classical?
No. The reason for detecting signal is very, very classical. So the fluctuation of mirror A or B destroys the balance of the interferometer of A and B and leak the photon or light to the mirror F and detector. So that's the reason, very classical.
So I didn't claim anything is quantum. I don't think I even used the word quantum. I don't know exactly. I didn't hear about any classical theory that is correct. So I'm just talking physics. I just want to know where the photons were. I don't know if they're like, they obey some, I don't know, magical rules.
It's really a naive question, but even when you cancel one port,
Cancel?
you're basically making a null condition for that port F, right? When you're null condition for that port.
What do you mean? Okay. So I'm
Yeah.
tuning, this detector is
So that
tuned.
but there's still a small amount of light, and if your C path is strong, there can be heterodyne
Yeah. So
signals.
yeah, this is experiment. There will be, of course, there will be leakage. Yeah. Any experiment?
That's not what you're seeing.
Huh?
That A and B, that's not what you're seeing.
So this leakage, you can kind of try to make it as small as possible, but you clearly see that the information coming from this mirror is absent here. So this is experimental.
But are you sure your tuning will remain intact in the presence of vibrations?
If I'm tuning this detector,
the tuning where you expect that at F there will be no photon. So does the tuning remain intact when you vibrate A, B, E, etc.?
Yeah, okay. Of course, the way I tune is only using PowerPoint, but the experimentalist that did this, he did the best job he could. Probably it's not enough. Probably there is leakage. With this, with modulation or without, there is leakage. But we somehow do not see these peaks here. So it kind of do something right. Okay, yeah. So now the question, can we do it with a single photons? Because as explained before, the data was getting from many photons together and then do some Fourier transform in time. But now we want to do it with a single photon. So single photon, we cannot get many photons and then Fourier transform them back. I want to use them separately, not sort of compare one to the other. So now I want somehow to put my information in a single photon. So is that possible? So according to Jun Chan, yes. This is the guy that built this experiment. And the idea is like this. Okay, first of all, of course, we need single photons, and we do this with the down conversion. So this is so-called the heralded photons. And then we build a nested interferometer, and we spread around these EOMs. So what the EOMs, they put some frequency component in a single photon. So the idea behind this experiment is very simple. Think I have a ball, let's say a cricket ball, and I have a system of tunnels which I cannot see. I throw the ball and I see it come out for some tunnel. This is how you play cricket, right? So now I want to know in which tunnel the ball went through. What would I do? So for me, the simplest solution, I will put some paint, let's say some fresh paint in the tunnels. I will throw the ball and see which colors the ball have on the other side. And then I will know in which tunnel it went through. Okay? So this will give me, without knowing what happened, I don't know if the ball sort of hops in tunnels or slide or roll. But I will know, just by looking at the colors, where have the ball been. So this gives me operational definition of trajectory. Which colors that I see, that gives me my trajectories. So now how this kind of is being executed. So I guess a lot of people haven't heard about this electrical optical modulator. So I'll just spend one slide explaining what they do. I have my single photon, I have some wave packet, I have the amplitude which is oscillating. And if I Fourier transform it, you probably know that I get the frequency and I get some widths related to this time. Now I have this magical machine that changes the refractive index with time. I connect this to some oscilloscope and get this sinus dependence in the time domain. I put my photon through this device, and I get this phase accumulated. Now when I Fourier transform, I find these small peaks, which I can control their size by controlling this parameter here. So this, now I marked the photon. This is a single photon, right? I'm talking now on a single photon sending to this machine and now having this spectrum. I kind of, so literally I put some color on that photon. Okay? So when I do this, of course, if I don't tune the interferometer, I can see all the peaks. When I tune, 2 peaks are missing. So again, according to my operational definition, without knowing any physics, I conclude that the photon was in A, B, and C, and not in E and F.
On the missing frequencies are E and F, what makes you think that photon has not been at E and F? Because concluding that it has been at A, B, and C is fair, but concluding that it has not been at E and F is not justified.
But
Because it is possible that it lost the information about E and F during the flight. Somehow it depends on the setup of apparatus, and it lost the information about E and F.
so, okay, this is a very interesting theory. I'm putting some information here. The way I put the information, I was very sort of clear about. And if somehow it kind of lose this information here and here, I will be really interested to understand this mechanism. Because the information was in there, and of course, the information from here was not lost. Why the information was lost from here?
Because the interference is happening in the spatial mode. And in spatial mode, so what you are doing is the phase modulation, and due to the phase modulation, the wave functions are destructively interfering. So the information about E is information about E passing through A and information about E passing through B is destructively interfering near the mirror F. That's why the E and F are missing.
But so
If you mark if you modulate the internal degree of freedom of photon as I presented in the poster, you will find the frequency about E and F.
if I did modulate the frequency here.
So the phase modulation is done on the wave function of photon, right?
Yeah, on the wave function.
Yeah, and wave functions are destructively interfering near F, near the mirror F.
Okay, the interfering, sure. It could be that all these words are correct, but I'm putting some information here which I did not get here. So
Because you are marking the spatial wave function, that's why it is missing. If you mark on the internal degree of freedom, it won't vanish. You will get.
So of course, if I'm writing this information on paper here and then I read it, of course I will get it. But I want to see if the photon is more, not other degrees of freedom.
So what if you looked at the other output of the interferometer? So what if you looked at the other output of the interferometer going down?
So there, well,
Okay.
I think here you would see probably all frequencies.
Yeah.
But then, yeah, you could think about many sort of.
So then your argument would have to change, maybe, or.
No, so far my argument was just I have a definitional operational definition. If you build some other sort of network.
I'm interested to see the other cases, actually.
Okay, so I can see one more case. I blocked C. So now I get from A and B, but not from E and F. So simply the photon was here, but not here, not here, not here.
In the original Weidmann paper, the counter was down there where this yellow thing is.
Yeah, and
does it matter?
they did not get these 2 peaks. They get, when they blocked here, they got, everything was 0.
So it's the same experiment. It was a different experiment from Weidmann.
It's a different experiment,
Okay.
of course, and a different result. And of course, you know, I think our actually is more, yeah. I like ours better, but it's like, I could say that actually it agrees more with the two-state vector formalism, which until now I haven't said, but there is a very simple way to calculate these trajectories. The one that I sort of showing here It's just calculated with the two-state vector formalism. But what I'm presenting now is just I have operational definition and I'm presenting the result. No theory, no sort of no fun endings. Okay. So how much time? So okay. So turns out some people are not really happy with this picture of non-continuous trajectory. So maybe you would like to have realistic trajectories. So you're in luck. This guy, Bohm, can offer you a completely sort of continuous realistic trajectory. The photon went from here to here, and this can explain any experiment you can think about. So you might be very happy, but there is a price to pay. So you all know that Bohm theory is non-local. But I think some people take this non-locality a little bit lightly. This non-locality is nothing to mess with. It's not the same non-locality as quantum mechanics. This is real non-locality. So what I'm saying, this is a very nice trajectories. But can we change them from a distance? If you take, and I'm dogmatic. I'm now taking Bohm message very seriously. The particle went here. So if the particle really went here, can I change the trajectory of the particle from far away? In other words, can I steer it? And I think actually this is a more correct way of using the word steering. And this was kind of a half nod from the steering inventor. Could I? Yeah. Okay. So can we steer these trajectories? So Jinshi and Chao-Ya said yes, and they built this setup. So now I'm taking two entangled photons. One of them I'm sending to a two-slit experiment, and the other I'm measuring in a different location. Okay? So now my decision to measure this photon will change the trajectory of this photon. So what happens? I have my sort of entangled pair. One of them comes here to this lab. The other one comes here. So it's 5 minutes. Okay, yeah. There'll be lots of time for more questions. This is almost the last slide. So the photon is traveling according to this trajectory, just as Bohm told him to. Okay? But now, Chao-Ya in this side decided to measure the other photon. Okay? And got some result. So what happened to this photon? Depends on what her decision to measure and on the result, suddenly the photons go here and there. So this is completely sort of a remote control of the particle from far away. So non-locality at its worst.
How far can you say?
So
what was the distance?
So okay, in the lab the distance was not like, you could, if Krista will repeat this experiment, he can do it like to close all loopholes and so on. But this can be completely instantaneous action at a distance, breaking everything that relativity tells us.
Just I wanted to know, in your lab, what was the distance?
I think it wasn't that far. I think it was like 1 meter. So yeah, we didn't sort of close any loopholes. But that's kind of what the theory tells you. If you take Bohm theory, it tells you the particle will just travel according to some trajectory, and then suddenly, poof, it will go in another direction. So that's the price to pay for a realistic trajectory. So now, everybody have the kind of their own choice. You want to choose reality, you have to swallow non-locality. you don't like non-locality, you think somehow Einstein was correct in his relativity theory, then you have to swallow these kind of weird trajectories. Or you can come up with something else. So I don't have any conclusion, but instead I will give you some of my favorite quotes. The more success quantum theory has, the sillier it looks. If quantum mechanics profoundly shock you, you haven't understood it yet. I think I can safely say that nobody understands quantum mechanics, and quantum theory has many problems. Hardgamers.com. Thank you.
Thank you for the stimulating questions.
Everybody
Comments.
agree?
Sorry, can I just ask, there's one thing I didn't understand. Can you show the slide with the detector, the first one? Go back, 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 back. Yes. The beam splitter do not reflect anything back. They just divide the photons, right?
Yes.
Nothing goes back. So we say when, are you sure that this is the correct? I mean, because going through EA doesn't lead you to the detector at all. You go out.
If you go.
I mean, if you connect it. I mean, in the original Weidmann research, it was connected there by a beam splitter, but was not traveled. That's a different experiment again. So.
No,
I know, but it seems I may be wrong. But my suspicion is, yeah. Well.
So.
Okay, fair enough. I don't understand this. Probably I have to think about it again. But how can a photon, which go out and traveled A and B, arrive in the detector?
So here. So okay, the kind of, I think the path you're looking for, if the detector come out from this port,
yeah,
and then it's projected here, reflected, and then to the detector.
Yes, but.
So here there's no beam splitter. The beam splitter.
I mean, if you don't care whether you have the photon in the detector or not, then of course you would have all the three peaks. But if you conditioned on having a detector, it seems to me, I may be wrong, probably wrong, but it seems to me on the thing that only the C signal would be observed in this setup.
I don't like this. This is the experiment setup, but this is the observation.
Also similar to a comment made earlier. So if you look at the other port,
yeah.
That port, do you expect to see EMF and not AMF?
So from this port.
So just by keeping the mirror phases, of different kinds, do we expect to see ENF there and not ANP?
I think here actually you don't see ENF. Yeah, I think here actually you don't see ENF. No. Huh?
All the light that goes in has to come out. So if there is essentially the lines are missing, the ENF lines are missing.
But there's no, like, you cannot add the light from E and A, right? It's the same.
Yeah. No, I just want to answer, maybe Dimitri, and just to point out some confusion. Here in this experiment, so there is some leakage that goes through F, and this is how the power spectrum is detected. But to see the effect that we want to see, you don't need this. You can have another type of setup, or you will see also paths that are not detected at E and F, although you don't have any sort of vanishing interference, quasi-vanishing interference on the path going through F, which is the case here. So this is a bit of a confusion. You don't need this effect, this vanishing interference to run the argument. This is what I want to point out.
Is talking to you.
In abstract and in publication, you invoke the two-state vector formalism to explain the results.
Yes.
Why did you not use here?
I thought I didn't have time, but if you want, this is So this is the two-state vector. This is the forward going, and this is the backward, and basically we're saying the overlap is
Yeah.
the
Now my question is that if some experiment is not agreeing with the prediction of two-state vector formalism, what will be your conclusion?
So, like, this will very surprise me because I thought this was a formalism. So what you're saying, it's not a formalism, right? Formalism means it's quantum mechanics written in a different way. So either okay, two options. Either quantum mechanics is wrong or this is not a formalism.
That's what I wanted to know.
Okay, I don't see.
Yeah, I have a question about the single photon data. I'm a little confused.
Yeah.
If you go back to that.
This or this?
No, the other one, the following one. Ah, okay, sorry, okay, everything is all right.
Okay.
No, I have, okay. So it seems that the Mach-Zehnder interferometer is tuned so that all the photons comes out to the detector, right?
So, okay, okay.
Did I understand correctly?
Maybe this is very confusing. This is not the detector. This is some other thing. This is the detector.
Ah, okay.
Yeah, I'm sorry. I should. This should not be there. It's something that the experiment used.
Otherwise, it wouldn't make sense. Okay, thanks.
Okay, I'm afraid
I think.
time's up. So let's discuss.
Just last question. What will happen if you remove the beam splitter F, mirror F from the system?
Which one?
Can you go back to that Mach-Zehnder? The mirror, before.
Here?
Yeah, even before. Yeah, here. Suppose you remove F.
Sorry.
What will happen if you remove F?
Remove this.
Yeah.
I will get only C.
Yeah, so the photon is seeing F.
No. This is the same logic that we started with. I'm blocking a slit, and then I'm saying, okay, it has to be in there. But we see that this logic doesn't work. Right? This was my third slide. This logic, which sounds wonderful, doesn't work.
Okay. So, time's up. So let's start the